Hey guys, hope everybody's doing okay. What we're going to do today is look at different types of chemical reactions. This is definitely one of my favorite lessons in this unit and really in the entire course. When you think about chemistry, you usually think about chemical reactions, right? You think of color changes, you think of things reacting and making some cool visuals or sounds, right? And this is where we get to take a look at some of those types of things. So there are a lot of different videos and demonstrations that go along with this lesson. This is going to be the basics that we'll go over in the video lesson today, and I promise when we get in class, I'll show you all the little video clips and demonstrations that I have planned for this lecture. All right, so we'll go through and it matches up with our note sheet pretty well. There are 5 main types of chemical reactions we're going to look at. There are labs associated with 2 of these that we're going to do later on in the unit, and there are, like I said, there's some videos and demos that really cover a lot of the other ones. So I think this is really interesting, and it's where everything that we've been doing so far kind of starts to pay off, especially the nomenclature part of it. We're going to look at how we write these chemical reactions and what categories they fall into. So without any more delay, let's get started with this and take a look at our first type of chemical reaction, which is a synthesis reaction. Another name for a synthesis reaction is composition or a combination reaction. Okay, so what I usually like to do is call them synthesis reactions because I like to categorize them based on what letter they start with. I tend to not use composition or combination as much because we have another reaction type that starts with the letter C that sounds similar and we could get confused by that. Okay, so what happens with a synthesis reaction? What really happens here is 2 or more substances combine to form a single, more complex substance. So for a lot of these, I have a little animation here for you. So on your note sheet, you can start with your pictorial representation here where we have 2 different substances. So these are going to react and make some product, okay? So what you want to do is think of what's on the screen, these two circles. This is your reactant. These are your reactants on the left-hand side of your equation. Then, so you could draw this, you can put a plus sign in between if you want to. Put a yield sign, and then the animation will occur, and we'll see what happens. Okay, so we have simple substance 1 and simple substance 2, these 2 different circles, and the animation goes, and the reaction happens. Okay, and we're left with our product. So that's what should be on the yield sign, like after the yield sign on your note sheet. So you basically have something like this. You have this plus this yields this. Okay, so yours will hopefully be a little bit neater than that, but it gives you a visual of what is going on here. Okay, so that takes care of the visual for a synthesis reaction. So some examples that we have are mercury plus oxygen. We have 2 elements here combined to make mercury oxide. Okay, HGO. Now some of these are balanced already, so this one is. We have 2 mercury atoms on the left, 1 oxygen molecule on the left, and 2 mercury oxide compounds there. 2 of those on the product side. Okay, let's take a look at another example you guys have on your note sheet, and that is silver plus sulfur. Okay, so we have a metal and a non-metal here, and we're going to create something called Ag2S, which is silver sulfide. So you're looking at this and you're like, why is, this is balanced already, first of all. But you're saying to yourself, why initially was there 1 silver over here, and then we have the 2 over here? Like, why isn't the product just AgS? Well, all goes back to your nomenclature and writing formulas. So you know silver is Ag plus 1. You know sulfide is S minus 2. So you're never going to just have AgS be created, right? Because silver is a plus 1 and S is a minus 2. So they need to be Ag2S. Okay? So when we write our products, we still have to make sure we follow our nomenclature rules and our formula writing rules to write them correctly. And then we balance the number of atoms we have with our coefficients. That's why the 2 is going to end up being over here on the reactant side in front of silver. Okay, so these are 2 quick examples of synthesis reactions. I think there's one more on here that has the word equation for us. So let's go through and do that real quick. Potassium plus bromine. So if you're writing the formula for this, potassium is obviously K. Bromine ends in INE. It's one that should stick out to you as one of our diatomics. Br2. Yields. Another metal plus a nonmetal here. This will make a basic a salt here. So potassium bromide is our answer. Potassium is K plus 1. Bromide is Br minus 1. So we have KBr as our formula here. Now we need to balance this because we have 2 bromines on the left and 1 on the right. So we balance it by putting a 2 there, 2 here, 1 here. So 2K plus Br2 yields 2 KBr. Okay, I have a video of that one. I'll show you guys that in class. But another basic synthesis reaction. So look at the pattern here, guys. We have 2 reactants coming together to create one singular product. And all synthesis reactions will look basically that way. Decomposition reactions are basically the opposite of what we just did. So a synthesis reaction or a composition is putting 2 things together to create one. A decomposition reaction is when you take one thing and break it down into 2 or more things. So a single substance is broken down into 2 or more smaller substances. This is important, so make sure you take a note of this. This is typically an endothermic process, meaning that they require heat or energy. Not every decomposition is endothermic, but a lot of them are, because it takes some work to break down the singular, the single substance that you have. So this is the only reaction type where we start with only one reactant. It's very easy to figure out what a decomposition reaction is because it's the only one that starts with one reactant and one reactant only. All the other reaction types start with more than one reactant, so decomposition reactions stick out pretty easily. So here's your pictorial representation. You're going to have just your compound to the left of your yield sign, so you can draw that, and then your yield sign. The animation will occur here, and then you can draw what the products are. So let's take a look at it. Here's our animation. We have our heat being added because it's endothermic, so our energy's going in. And it helps break apart our substance into 2 simple, smaller substances. So this would be after your yield sign. You would have that circle plus that circle. Okay, for your pictorial representation. Let's take a look at a couple examples here for this. There's the demo I'll do in class. That's really neat. I'll show you guys that when I see you again. So here are your examples. You have KClO3 plus heat. Students get thrown off by the plus heat here. That plus heat, there's no chemical for that. Plus heat just means energy is being added. Another way to write that is if you don't have it in the equation here at all and you have your delta H above the yield sign. All right, so potassium chlorate is going to break down into potassium chloride and oxygen. Now we need to balance this. We'll eventually be able to write these products on our own, but right now we're just looking at the types of chemical reactions. I'm not teaching you how to actually do all this yet. So we want to balance it, put a 3 in front of the O2, a 2 in front of the KClO3, and a 2 in front of the KCl. Okay, so we should be okay at balancing equations by now. On your note sheet, I think it has MnO2 up here. It should be a delta H. Okay, there's MnO2 is a catalyst for a different reaction. So here's another one, BaCl2.2H2O. We did this last unit where we have a hydrate. You add heat to that, and the hydrate breaks apart into the anhydrous salt and water. So these are very easy to identify because the water just breaks off. You have the water going into the air basically. So what we have right here, and the plus sign represents that those 2 things are now separate. Here's the demo I'm going to do for you. Hydrogen peroxide breaks down into water and oxygen. So again, we have one reactant, one reactant, one reactant breaking up into our products here. We have 2 products here, 2 products here, 2 products here. So you can see the pattern here for decomp reactions. Let's take a look at this one we just did and balance it. We have a 2 in front of hydrogen peroxide, which is H2O2, and 2 in front of H2O. I think that should do it. Last one, there's a catalyst for it. Sorry about that. The catalyst I'm going to add in school when I do the demo for you is potassium iodide, Ki. You'll also see the heat for this one is given off. So this is one decomposition reaction where it's not endothermic. Most of them are. You can see the first one was endothermic, second one was endothermic. This one's actually exothermic because the heat is a product. The reaction will get hot when I do this, and I have a really neat video of this. I'm going to actually do a version of it, like I said, in school. This last one is a video associated with this as well. I'll show you in school. It's nitrogen triiodide. So using our nomenclature rules, nitrogen triiodide is Ni3. You add a little tiny bit of energy to this, very minuscule amount. You'll see that in the video. And you create nitrogen. N's in GEN, so it's diatomic. It's N2. and iodine ends in INE, diatomic, it's I2. So we have to balance this. Let's put a 2 here, 1 here, 3 here, and that should take care of it. So 2 nitrogens on both sides, 6 iodines on both sides. Pretty easy to balance that one. Again, starting with 1 reactant breaking up into 2 products. Easy. Decomposition reactions. The next 2 are very related. They are single and double replacement. Let's take a look at those. Single replacement reaction is when we have a compound and an element. So a single element takes the place of another element in a compound. So here is your compound, and here is your element. This one's always going to be an element plus a compound, and we're going to see what happens. So let's take a look at the animation here. So basically you have your compound plus your element, and then there's your yield sign. Let's see what happens with the animation, and you'll see what your product should be. Single element comes in, kicks out another element in the group. Okay, so again, one more time. Watch our single element here, that blue circle, take out the gray circle. Comes in, there we go. All right, so that's your product. Well, those are your products, 2 of them. Okay, so you're going to create another element and a compound. You just have some things switching places. All right. So you're always going to start with an element and a compound here. And here are some examples for you. I'm going to do this demo in school. This one's really neat. I'm going to have a little bit more than just zinc and hydrochloric acid, though. I'm going to do something with that. You have zinc and hydrochloric acid. Your zinc is the element that is on its own, and it's usually a positive ion, right? Zinc is a +2. Positive ions replace positive ions. Negative ions replace negative ions. And we'll go over that more when we do the single replacement reaction lesson. But it's going to replace the hydrogen. Okay, so let's take a look at what happens here. The hydrogen ends up by itself. When it's by itself, it's diatomic, H2. And then you make ZnCl2. You're wondering, why is it ZnCl2? It's because zinc is Zn with a +2 charge, and chloride is Cl with a -1 charge. So you have to put those together to make ZnCl2. We balance it by putting a 2 in front of HCl. Okay. Another example, sodium plus water. Very neat reaction here. I might show you this. I'm going to show you this actually later on in the course, where it's a little bit more appropriate to show that when we do periodic trends. But another way to write water is HOH. I'm doing this with my AP kids right now with our acid-base unit, and it's easier to see how the water reacts with your ion, or with your metal in this case. So sodium's a +1, hydrogen's a +1. So it's actually going to replace that hydrogen there. And look what you end up with. If the sodium comes over here and replaces that hydrogen, you make sodium hydroxide, NaOH. So you have your OH left over. You know, Na is a +1, OH is a -1. And then the hydrogen comes over here, right? And the hydrogen's by itself, so it's H2 now. And we just need to balance this. 2 in front of HOH, 2 in front of NaOH, and a 2 in front of Na should take care of it. All right, that's another single replacement reaction. Element takes place of another element in a compound. All right, same thing so far for these. Now this one is ferric oxide plus aluminum. This is called a thermite reaction. It's a really, really neat reaction. And I have a video clip of that one that I'll show you guys in class. But let's take a look at it. Ferric is iron, right? So you want to know the aluminum is going to take the place of the ferric, which is the iron. Okay, what will we end up with then? We'll end up with iron by itself plus aluminum oxide, since the iron, which is ferric, and the aluminum switch places. Okay, so aluminum oxide plus iron. And we can write the formula for that as well. And we'll go over that in class when we actually do that reaction here. Okay, so you'll need your cheat sheet to know what ferric is. Is that iron with a +2 or iron with a +3? And then it's pretty easy to write our formula and balance that. All right. Second to last one, double replacement, very closely related to single replacement. You might be able to get an idea of what this is all about just by looking at it. So this is also called an exchange or metathesis reaction. I very rarely use those, but I just want to make sure I point them out to you. That could also be called this, but I usually go with double replacement. It's nice and easy to understand that. So here's what happens with a double replacement reaction. You have two aqueous ionic compounds switch partners. So this is similar to single replacement, where things are switching partners or switching, where they are in the chemical reaction. But in this case, we have two ionic compounds, so two compounds in general, compared to single replacement, which was an element and a compound. All right, single replacement was element and a compound. Double replacement is compound and a compound. Both reactants have to be aqueous in order for this to happen. So you'll have aqueous, a little AQ in parentheses for both of these on the reactant side. So here you go with your pictorial representation. You have compound number 1 on the left, compound number 2 also on the reactant side over here. So you have these two compounds and your yield sign. Give you a second to write that in. And then the animation will occur and you'll see what you're going to write on your product side. So let's check it out, see what happens. Okay, one element in each compound switches partners. Okay, so here we go. One more time. All right, so this is going to be after your yield sign. We'll have those two things. So compound plus a compound yields compound plus a compound. So you're always going to start with two ionic compounds. A little repetitive here. A couple examples. You have silver nitrate and sodium chloride. So just like single replacement, your positive ions which would switch with positive ions. Same thing here with double. So your positive ions are your silver and your sodium. Okay, they're going to switch partners. So the sodium will come over here, and the silver will come over here. So you'll make sodium nitrate and silver chloride as your two products. Let's check it out. AgCl is your silver chloride, and NaNO3 is your sodium nitrate. Okay, I just put them in a different order on here, but it doesn't really matter what order you put them in. You could have put NaNO3 first and AgCl later. This is already balanced for you, and notice that I have states here. These are important, so put those in on your notes. We're going to learn how to get these correct states of matter later. Okay, so we'll do that in a different lesson. Here's another one. We have calcium chloride and potassium nitrate. So calcium chloride is CaCl2, aqueous, and potassium nitrate is KNO3, aqueous. The two positive ions are calcium and potassium, so they're going to switch partners. So you'll end up with potassium chloride and calcium nitrate. Okay, so what do they look like? We're going to have KCl, aqueous. I know that's aqueous because I have solubility rules memorized. You'll know that in a couple days. And then calcium nitrate, CaNO3 is also aqueous. All right, gotta balance it. So we should put a 2 here, 1, 1. I think that takes care of it. All right, so calcium chloride and potassium nitrate, you have two aqueous ionic compounds to start. Your positive ions switch partners. You rewrite your formulas with your nomenclature rules, and you're good to go. So you start with two ionic compounds, and you're really ending with two ionic compounds as well. Last one, sodium iodide plus lead-2 nitrate. So the sodium and the lead-2 will switch partners. And you'll create sodium nitrate and lead-2 iodide. Okay, so formula for that, sodium iodide, NaI, aqueous, plus lead-2 nitrate, PbNO3, aqueous, yields lead-2 iodide, PbI2, and that is a solid actually. That is going to be the video clip of this I show you in class. And sodium nitrate is aqueous. NaNO3. All right, got to balance it out. Let's do 2 in front of NaI. Let's do a 2 in front of NaNO3. And I think that's it. Yeah, looks good. All right, takes care of double replacement. Last one is usually students' favorite reaction type, combustion reactions. So what happens here is a hydrocarbon reacts with oxygen to produce water and carbon dioxide. This is a really easy reaction type to identify because you always start with a hydrocarbon. Believe it or not, a hydrocarbon contains two elements, hydrogen and carbon. Okay, so that's not too hard to identify there. And it's always going to produce the same two products, water and carbon dioxide, so H2O and CO2. Most fuels are hydrocarbons. That's why these reactions are so important. And we've been talking about some energy and climate chemistry, so we know a little bit about this already and the combustion process already. So it's used by modern society to create lots of energy and heat, which is an exothermic process. So that's really, really important. Lots of heat and energy is given off. That's why we have exothermic there. Okay. Here's your pictorial representation for this one. So you could write that down as I make sure my mouse is working here. Some hydrocarbon, which is what we have right here. Okay. Plus oxygen, O2, this is diatomic, gives you H2O and CO2. Those are always your same two products. Okay, so take a second and jot that down. Here's a tip for balancing combustion reactions. It's going to be carbon, hydrogen, and oxygen. So if you balance them in that order, everything becomes a whole lot easier for you to understand. So here's CH4 plus O2. Here's your hydrocarbon, CH4. All right, and then plus O2. That's your oxygen, obviously. And what's that going to create? Well, it's going to create the same two products every time. All right, same two products every time for combustion reaction. H2O, CO2, and a lot of energy. You don't usually need to write the plus heat over here on the product side, but if you do, that's okay. All right, just know that you don't have to put it there, but you should know that it's a very exothermic process. All right, balance it out. We should do our carbons first. There was one on each side, so hydrogen goes next. Put a 2 in front of the H2O, and oxygen last. We have 2 oxygens on the left, and now we have 4 on the right, so you put a 2 in front of the O2 to balance that. Okay, next one is ethanol, it looks like. Ethanol has 2 carbons in it and an OH group at the end. That's how I know that. That's some organic chemistry stuff you'll do if you ever take that course. So it's still hydrocarbon, C's and H's, plus O2. Yields what? Well, combustion reactions have the same products for the most part. You have H2O, CO2, and heat. Let's balance it out. We need 2 carbons on the left. That's what we have. So we have to put 2 carbons on the right. Balance carbon first. Hydrogen goes next. We have 6 of them on the left. We only have 2 on the right, so you put a 3 in front of H2. And for oxygen, you have 3 on the left. Pay attention to that. You have 1 right here, and then 2 here. And that makes 3. And on the right, you have 4, 5, 6, 7. You have 7 on the right. So you want to put a 3 in front of the O2, gives you 6 oxygens there, plus the 1 here gives you 7, and you're done. Putting a coefficient in front of the ethanol messes up everything all over again. Okay, so follow the rules, carbon, hydrogen, oxygen. You'll be good to go. All right, really, really neat combustion demonstration I'll do for you guys in class once we get back at school. And I think you guys will enjoy that. So that's basically your combustion reaction overview there. That takes care of it for the 5 reaction types. There's a very quick lecture on that. It takes a little bit longer in class with the videos and demonstrations, but it'll actually work out pretty well because you will be able to get the notes right now. Then in class, we can do all the videos, demos, and review them, and we can work on some of the homework that we have associated with this. Okay? So the assignment right now is to make sure that all of your reaction types are filled out in your packet, and then we'll be able to work through some demos, videos, and practice problems a little bit later. Okay, there's a flowchart at the very end of your packet on the last page that goes over how to identify and write products for all the different reaction types, synthesis all the way through combustion, if you want to take a look at that. Okay guys, that takes care of it. Thanks.